Okay, students, I hope you are all well and healthy and ready to learn the new things. So, my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education and Research Center, Navsari, in Civil Engineering Department. I am going to teach you the subject is Design of Reinforced Concrete Structures. In this subject, we complete Module 1, which is G plus 3 RC building and structural layout. And in Module 2, we are going to learn retaining wall design. In the previous lecture, we covered introduction and cantilever retaining wall design. In the introduction portion, we complete a theory content like force on the retaining wall, and failure of retaining wall. So this type of theory we completed in the introduction portion, and cantilever retaining wall design is completed. So in this lecture we are going to learn counterfort retaining wall design. Counterfort retaining wall design. So you can see here is a counterfort. So by this you have to design this retaining wall with counterfort connection. They are just change in a load distribution, load transformation, and by the load transformation design method is changed, right? So let's start. Counterfort retaining wall design. We have an example here. Design and detailing. Okay, I don't have to read it. Okay, just read it. Design and detail counterfort retaining wall for the following data. Where is angle of response is 30, unit weight of soil is 60, height of wall above ground level is 7, safe bearing capacity of soil is 150 kN per meter square, coefficient of friction between base and soil is 0.6, and use M20 grade of concrete and Fe415 grade of steel. Okay, so this is the example by the we are going to learn counterfort retaining wall design. Okay, so now you can see let's change a pen here. So design the counterfort retaining wall. Here is the example 1 which you read earlier in the presentation. Now design and detail counterfort retaining wall for the following data: 30, angle of response 30 degree, unit weight of soil 60, height of ground level 7, safe bearing capacity 150, and coefficient friction between base and soil 60, M20 concrete and Fe415 steel. We read all the data earlier. Now we have a solutions. A coefficient of earth pressure. Okay. Coefficient of pressure. We have to calculate coefficient of earth pressure, which is phi is 30. Phi is 30 is given, right? Angle of response is given. Ka and Kp. What is Ka and Kp? We discussed this earlier lecture in the cantilever retaining wall. So Ka is active earth pressure coefficient and Kp is passive earth pressure coefficient. Ka equation is 1 minus sine phi divided by 1 plus sine phi. So is 1 by 3. Sine 30 and sine 30 we found value 1 by 3. So Kp is equal to 1 by K. So it's 3. Now we have to decide a preliminary dimension. First of all, we have to decide dimension of a stem as well as slab and counterfort. So we have gamma is 60 kN meter cube. Where is given? Here. Weight of soil is given 60. Same thing, by the 60 SBC of soil is 150 kN per meter square. These both things are given. So by this both value we have to find out minimum depth of foundation is D minimum Q0 Q0 is equal to say SBC of soil Q0 divided by gamma into 1 minus sin phi divided by 1 plus sin phi whole square. So put the value in equations. Q is 150, gamma is 60, so 1 by 3 whole square. So D minimum is 1.04, so 1 meter. So minimum depth of the foundation is 1 meter. We require 1 meter depth foundation. So overall height of wall is H is 7 plus 1. Why this 7 here? Because we have to given in the example there is a height of wall above ground level is 7 meter. Height of wall above ground level is 7 meter. So 7 meter plus 1 meter foundation, that means 8 meter height of a stem. Right? Now base width. Base width may be taken as 0.6 to 0.7. Okay, is imaginary. 0.6 h to 0.7 h. 0.6 h to 0.7 h. Base width is comparison with the height. Base width is comparison with the height. So base width is B is 0.6 h to 0.6 into 8. So 4.80 meter to 0.7 h. 0.7 into 8 to 5.6. So by this two value 4.8 and 5.6. So base width in between these two value 4.8 or 5.6, we have to provide in between these two value. So we provide a base width is 5.20 meter. Provide base width is 5.20 meter. Right? Now we have to decide toe width. Toe width may be taken as 1/3 of the base width. Means we provide 5.20 meter as a base width. So toe width is 1/3 of base width. 1/3 of base width. So it will 1/3 into 5 by 2. So value is 0.7 meter. Maximum toe width is 0.7 meter. Now we have to decide thickness of base slab. Thickness of base slab. So thickness of base slab is equation is h by 50 or h by 20. Thickness of base slab is h by 50 or h by 20. Height is 800. Height is 8000. Okay. Yeah. So height is 8000. 8000 divided by 50 or 8000 divided by 20. So by this two value, 5.33 to 40 mm. Provide thickness of base slab is 450 mm. Right? So now we have our stem height and as well as base dimension is final. Now we are going to provide counterfort. So we have to calculate spacing of counterfort. So we have two conditions here. For the counterfort, we have two conditions. First is provide 3 meter to 4 meter center to center spacing. 3 meter to 4 meter center to center spacing. Or for an economical design, the clear spacing L between the counterfort may be determined by a relation. So there is a relation. 3.5 into h by gamma into 0.25. These are the calculation. If are you going to this calculation is enough, or follow this 3 to 4 meter. In the exam point of view, I advise you to go with this because this is the time consuming. This calculation will take a time consuming, right? So 3.5 into 8 by 68 is the height by 60.25. So value is 3 meter. So So we provide 3 meter center to center spacing of counterfort, right? Now we have to find the thickness of stem. Finalize the thickness of stem at a base is h is 0.8 minus 0.45 minus 0.45. What is this minus 0.45? Minus 0.45 is 0.45. It's a simple, it's a thickness of base slab. It's a thickness of base slab. So total height of a retaining wall is 8 meter. Minus 0.45 will be minus. Then after height is 0.75 meter. So we are going to design a stem for 0.75 meter. Now we have to find a thickness of stem at a base. So we have to calculate pressure at the bottom of a stem. So K into gamma into H. Pressure at the bottom of a stem. So K into gamma into H. So 1/3 into 60 gamma into H is 0.75. So value is 4026 kilonewton per meter square. Now we have to find out maximum bending moment WL square by 12 near support from IS 456 2000 table number 12. Let's check this thing in this. Okay students, so look at here. Here is IS 456 2000 table number 12 bending moment coefficient. So by this table we can find out bending moment at span and at support, at a span as well as support, right? I hope you understand how to read this in the DOS in the previous lectures. I understand these things in the continuous beam design or G+3 RC building design. Okay, bending moment coefficient calculation. You remember this thing, so I not waste the time for the explain these things. But you have to find this coefficient 0.12, 0.10, 1 by 10, 1 by 12, 1 by 60, right? And I will explain everything in the lectures, so I will not repeat it again. So you saw how we why we follow IS 456 2000 in the table number 12. So mu equation minus 40.26 into 3 whole square divided by 12. So mu is 30.20 kilonewton per meter. Mu is 30.20 kilonewton per meter. But we required a factor moment. We required a factor moment. Minus 1.5 into 30.2. So factor moment is minus 45.30 kilonewton per meter. So is a factor moment. So we are going to design by a factor moment. So we have to find in this example we are going to find the depth of the stem. Thickness, sorry, not the depth, thickness of a stem. But by this equation mu 0.138 FCK BD square, by this equation we can find out the depth. So mu is 45.30 into 10 raised to 6. Why? Newton per mm square. Newton per mm. So 0.138 FCK 20. Depth is 1000 because we assume a 1 meter thickness, 1 meter length of a stem. So 1000. So d square. So d is equal to 128.11 meter. Right? So for the shear criteria, we provide larger depth at the 2 times. Shear criteria means safety against shear force. We provide larger depth at the 2 times. Means we found depth is 128.11 meter multiplied by 2 and we provide depth is 250 mm. 250 mm. And remember, minimum depth is required 200 mm. Why? Because at the top of the slab, top of the stem, we provide 200 mm. That's why we require minimum dimension is 200 mm. So assume effective cover is 50 mm. So assume assumptions, right? So overall depth is 250 plus 50 means 300 mm, and provide top width 200 mm. Now heel width 5.2 minus 1.7. 1.7 is what? 1.7 is a toe slab. 1.7 is a toe slab, and 0.30 is a thickness of a stem. So heel width is 3.20 meter. 3.20 meter. So right now we require this drawing. Okay, let's draw this drawing and write down the dimension in it. Okay students, I completed a drawing. Now we are going to dimensions of it, right? So first is the stem top width is top thickness is 200 mm, right? And bottom thickness is 300 mm. Okay, toe slab width is 1700 mm, and here is 3200 mm. Heel slab width same is total height is 8 meter, but width thickness of base slab is 450 mm. So total stem height is 7550 mm, right? So these are the dimensions. But one more thing which we forgot about it. Okay, yeah, I'm not forwarding, I just neglect these things. Ground level. Here is a dimension is 1 meter height, right? This foundation height is 1 meter. So this point so this 1 meter height will affect on the toe slab. So we have to calculate all the load which affect on the retaining wall, right? W1, W2, W3. Let's check this in the. Now we have to find out stability calculation. We have to go find out stability calculation. So we have what to do. We have to find out W1 load, W2 load, W3 load, and W4 load. How all the loads are calculated, I will explain it. Just wait for it. Okay, in this file I have a horizontal load calculation. So I will explain this thing in the previous lectures. I think in the cantilever retaining wall I will explain all the things, how this load is calculated. So in this lecture I will not explain it again. It's just a repeated thing. These things just a repeated thing. Okay. So horizontal load, P horizontal load means this PA. This. So horizontal load is calculated 1/2 into 4.6 into 8 because of the triangle shape. So 179.86. So perpendicular distance 130 to 8 because of the triangle. There is a distance is 2.67 and moment is 455.15. Therefore, total pressure and total moment in the horizontal direction we have find out, right? And we got sliding force and overturning moment. Sliding force and overturning moment. I will explain how to calculate sliding force and how to calculate overturning moment. Now we are find out the vertical loads. Means a W1, W2, W3 downward, right? So density of concrete is 25, density of soil is 60. So load type W1 is 7.55 into 0.20 into 25 because of the concrete. So you can find out moment is 71.75. Perpendicular distance from A. Perpendicular distance from A. So look at here, W1 is here from a perpendicular distance, so we have to calculate this distance, right? So 0.7 plus 0.1 plus 0.1, so 0.90, so moment is 71.72. Now we have to find out W2, 1 half 0.1 into 7.55 into 225. So load here, moment here. Same for the W3, load here, moment here. Okay. W4, total load and total moment, right? I will explain detailed things in the previous lecture. You just go and watch these things. How to calculate W1, W2, W3, how to calculate the distance, how to calculate the moment, and why these things are so much important for this example. I will explain all the things in detail. So go and watch the previous lectures. I hope you can understand. If not, just inform me. Okay. Then after we found total downward force and total resulting force, so we can find out eccentricity E. How? B2 by x bar. So x bar is net moment at the toe, W into x bar. Net moment at the toe into W into x bar. So W is 492 and net moment 462.32. So x bar is 2.29 meter from toe. Why this 1632 minus 455? 1632 minus 455 here. Overturning moment minus resulting moment. Resisting moment minus overturning moment. Okay, this found a net moment at the toe. Imagine, okay, look at here. In this graph, you can say here is a point A. One is horizontal force from here and 4 downward forces. 1, 2, 3 and 4. So by this horizontal force, we can found at A moment in this direction. And by the downward force, moment by this direction. So by this 2 moment, resultant net moment will be changed, right? Understand? So this net moment is here, divided by weight, load. So eccentricity B by 2 into x bar. So eccentricity is 0.20 meter. So why we require eccentricity? Because we have to find out pressure at toe, which is maximum and minimum. W by B 1 plus 6E by B. W by B 1 minus 6E by B. So maximum has a plus, minimum has a minus. Simple. Both equations you can see. Sigma W by B, minimum, sigma W by B. If plus change, only plus and minus sign change. In a maximum plus, minus, minimum minus. Okay. W, B, 1 and all the data we find it. So put in the exam, put the value in the equation. So 117.62 meters square, which is SPC of soil, which is less than SPC of soil. SPC of soil is 150 kilonewton meter square, which given in the example. And minimum is 71.72 kilonewton meter square. These both criteria I explained it in the previous lecture. Okay, maximum is not more than SPC. Maximum P maximum is not more than SPC of the soil, and P minimum is not less than 1. Okay, these are the criteria will be fulfilled, means your retaining wall is safe against settlement, right? So retaining wall is safe. Now we have to find out two more safety factor of safety against overturning and factor of safety against sliding. Okay, so for the factor of safety against overturning, MR divided by M0. this value is more than 1.5, that means our retaining wall is safe against overturning. And factor of safety against sliding means restoring force divided by sliding force. So his value is 1.55, more than 1.55, thus retaining wall is safe against sliding. If these two criteria will be fail, is you cannot find a safety against overturning and safety against sliding, we have to change in the dimension of retaining wall. For the sliding, you can use a shear key. Shear key in the retaining wall. If fail, but here we found a safe, so we not required change in the dimension, or we not required a shear key. Okay. Now we are starting a design. First thing we do example. There is a, remember the steps here. We found out the dimension of the retaining wall, right? Then after we check the retaining wall dimension for the safety, and we found the retaining wall is safe, so we are going to design a stem, right? So stem in design as a continuous slab. Why? There is a change in the designing. Why? Stem is designed as a continuous slab spanning between two counterfort. Imagine the things. In the cantilever retaining wall, we design the stem as a slab only. But when we have found in the counterfort design, there is a stem is designed as a continuous slab. Okay. Why? If I have a figure here, look at here. You can see the figure. Here is a stem, and this is the counterfort. So imagine is the stem is behave as a slab and counterfort is behave as a column, right? So load mechanism will be changed. Your stem load is transferred here. In the cantilever retaining wall, stem behave as a cantilever slab. But in the counterfort retaining wall, stem behave as a continuous slab. So design method will be changed. We have just to design continuous continuous slab. Okay. So first of all, we have to find out pressure at a base Ka gamma H. Triangle shape, soil pressure 1/3. 60 gamma into H 7.55, stem height, so 14.60 kilonewton per meter square is the pressure. 40.26 kilonewton per meter square is the pressure. So by the pressure you can find out moment. I hope if we calculate this, 45.30 into 10 raised to 6 the pressure here. Okay. 45 30 into 10 raised to 6, so B is 1025 whole square, so 0.725. So here is the equation, PT into 50 FCK Fy1 minus 4.6 MU1 FCK BT square. So PT value is 0.210. So provide value in AST. So we found AST is 525 mm square. 525 mm square. So 525 mm square is a AST. So we provide 12 mm diameter bar at 210 mm center to center at support near counterfort in the horizontal direction. At support near counterfort in the horizontal direction. So this 12 mm diameter is provided nearer at a support. Now we have found at a mid span. So mid span's factor moment mu 1.5 W square by 24. This equation comes from the IS 456 2000 table number 12. So we are going to find out the moment. So moment is 22.64 after putting a value in the equation. So mu BD square PT. So PT is less than 12 mm, minimum required 0.12 percentage. PT is required minimum 12 percentage. So we found a 0.10, so we follow 0.12 minimum. Not provide PT is minimum 0.12. Okay, so PT is 0.12, provide PT is 0.12. So AST 0.12, so 300 mm square. AST 300 mm square. So provide 8 mm dia at 160 mm center to center in horizontal direction at a mid span on a toe face. On a toe face. Now we have find out the distribution still in the stem. We required average thickness and provide minimum 0.12. So AST is 300 mm square. It's fine. So provide 8 mm dia at 160 mm center to center in a vertical direction on a toe face. So these are the distribution still is completed. So I hope stem design is completed. And provide 8 mm dia at 320 mm center to center both way in the heel face. Right? So what design is completed? Stem design is completed. We provide enforcement at a support, we provide an enforcement at a mid span and distribution state. So our stem design is completed. Now we are going to find a check. Find a check for the shear. Maximum shear at a face of counterfort. So VU is 1.5 W by 2. When we find this, we find in the IS 456 2000 page number or not a table number 12. So VU is 18.52 tau V VUBD. So VU tau V is a 0.362. PT is 100 AST 1000 AST. So tau C is 0.34 by the PT. So tau V less than tau C means design is safe. I explained all the details how we find out tau V and tau C in the previous lecture. Previous lecture is so much time consuming because I explained all the things in details. But in this lecture I will just skip this thing because this is just repeated and repeated and repeated again. This is just repeated and repeated again. It's just a waste of time for you and as well as for me. Okay. Now we have find out the check for the development length. The horizontal bar in the stem at the support must be checked for the developmental length near the point of contrafracture. The shear force at the point of contrafracture at 0.151. Right. So V is equal to W by 2 W into 0.151. So V is 38.05 kilonewton. The factor load is 57.08 kilonewton. Now we have follow IS 456 2000 page number 44. Page number 44 to check the development length. So page number 44 we have (36). Here is the equation. So we use this equation here. mu1 VU plus L0 is greater than LD. Is greater than LD. So mu1 is 22.64 kN per meter. mu1 is 22.64 kN per meter. VU is 57.08. L0 effective depth is 250. So put all the value in equation. And LD is 47.5. So 646.64 mm in 47 point into 12. So 646.64. So this bar must be accepted up to point distance L0 beyond to point of counterfacture. Right? So we provide 700 mm length for the face of counterfort. We provide an extra bar at a counterfort. Okay, for the development length 700 mm. Now we are going to design a connection of stem with a counterfort. So stem is connected to counterfort by the two-legged horizontal stirrup to carry entire shear force. Okay, so stem and counterfort are connected with the horizontal stirrups. Now in the counterfort we have two types of stirrups. Okay, I explain in the drawing, just give me some time. Okay, in the drawing I will explain how this counterfort. Okay students, so you can see here, here's a stem, here's a base slab, and here is a counterfort. Okay, so this triangle portion is look as a counterfort, is as a counterfort. Now what we are going to understand, we are going to understand connection between counterfort and stem, as well as connection between counterfort and base slab. These things are important. These things are important because these both the things are used for the transfer load. If you imagine counterfort and stem connection are not very good, at that time what happened? Retaining wall will be fail. So how we connect between counterfort and stem? By a horizontal stirrup. By horizontal stirrup. You can see here is a green line is represent horizontal stirrups, and as well as counterfort is connection with the base slab by vertical stirrups. You can see the orange line is a vertical stirrups, right? So what we are going to do, we are going to design counterfort connection with the stem. Counterfort connection with the stem. So what we are going to design, we are going to design horizontal stirrups in a counterfort. And when we are going to connection between counterfort and base slab, what we design vertical stirrups in a counterfort, right? Simple things. I hope you understand. Okay, so you understand things, how we connect a counterfort with a stem. So horizontal pressure at any depth y from the top, so Ka is equal to gamma into y kilonewton per meter square. So 1/3 into 60 into y, so 5.33 y kilonewton per meter square. Y depth is not provided because the pressure will be changed when y changes. So by the effect of the depth, we can change the design at every single level. Okay, so take total shear force at y 2.7 meter, height of the stem. So in this calculation we are finding 2.7, sorry, okay, 2.7. so height of the stem, so factor shear force is 10, so total tension force is T, total tension force 0.87 into Fy. Okay, factor shear force 1.5, 40.39 y into 10 raised to 3. Okay, so AST is 59.78 y mm square. Y mm square. We found the AST at some depth. So this is y is here. Okay, y. So I put a y is 7.55. So at that time design is changed. If I put y is 4.55, that time again design is changed. And this changing design, you can see here, is 8 mm dia at two-legged horizontal stirrups, 220 mm center to center. But at a y 4.5, 6 mm dia, two-legged horizontal stirrups at 200 mm center to center. What happened? Reduction in the steel. That means reduce in the cost. So these concepts are used for the reducing the cost. That's why I did not provide We did not provide a depth here. A depth here. Okay. So here is a design is completed. Now by this design we can say, okay, from the top to left. Okay. I will explain in the figure. So give me some time. Okay. So now you can see here. Here I divide a stem in a two parts. One is 0 to 1 meter and second is 3 to 7.55 meter. Okay. So in the first part I provided 6 mm dia at 200 mm center to center. Okay. In the next we provide 8 mm dia at 220 mm center to center. Okay. So this is the distribution is completed, horizontal strip design is completed. Now imagine if I provide 8 mm dia 200 mm center to center in the whole structure, means in the 0 to 3 meter one part I provide 8 mm dia at 220 mm center to center, first part, in the first part. So that way cost will be increases. So what we done? I done 6 mm dia at 220 mm center to center on the top of this stem. Then after by the 3 meter, after a 3 meter depth, 8 mm dia at 220 mm center to center. So this will reduce the cost of the retaining wall construction, right? So here is a design is given. So 0 to 3 meter depth provide 6 mm dia at 2 leg stirrups at 220 mm center to center, and second one is 8 mm stirrups at 2 leg stirrups at 220 mm at center to center, right? Now we are going to design a toe slab. What we have to do, we have to find the load P maximum and P minimum here. So by the load we have to distribute this diagram. I explain this diagram how to draw and how to find all the data in detail, so I will not wasting this time. Okay, the design of toe slab. So toe slab designed as a cantilever slab. Toe slab is designed as a cantilever slab. Here is a force, here is same figure, same diagram, right? So pressure at D, difference, so 99.95 kN per meter square. P is 99.95 kN per meter square pressure at D. Okay. Okay, in this graph, these things happen. Okay, here 99.95. Same thing at a pressure at C. Pressure at C means at here. So 102.60. I explain all the things in detail, where how to find pressure at C, how to find pressure at D, and why this is important, right? Now we have to find out total downward pressure on a toe. Total downward pressure on a toe. So self weight of toe slab is 0.45 into 25, so 11.25 kN per meter square. In the toe slab we neglect a soil. We neglect a soil pressure which is above on the toe. We neglect these things, so only calculate self weight of toe slab. So bending moment and critical section 91.35 into 1.7 into 1.7 by 2. Why this happened 91.35? Here. This diagram 91.35. And the second diagram is this. So by these two diagrams we can find out maximum moment at a toe. So 91.35 plus 1 half into 1.7 into 50 into 2/3 into 1.7. So 146.45 kilonewton into meter. Factor bending moment mu 1.5 into 146.45. So factor moment is 219.68 kilonewton into meter. right? Now for the toe slab, D is equal to 45.50. It's the depth, it's the overall depth. So we provide 50 mm cover. We provide 50 mm cover at a toe slab. So 400 mm is the overall thickness, actual thickness of the toe slab. So by this actual thickness we found mu, then after PT, then after AST upon PT. So we provide at toe slab, provide 20 mm dia at 180 mm center to center at the bottom face of the toe. Then after we have to find our distribution still, provide 20% of cross section. So AST. So for the distribution steel we provide 10 mm die at 450 mm center to center. We provide distribution steel is minimum 0.12% PT, right? So for the control of crack, provide 10 mm dia at 280 mm center to center. We just multiply this distance, by 2. Now check for the shear. We have to follow all the times, just check for the shear all the time. We have to follow some check. So shear force at critical section 91.30 is 1/7 into 1/2 into 1/7, so 168.04 kilonewton. Factor of safety VU is 1.5, so 252 kilonewton. So 252 kilonewton we can find out tau V, then after PT, then after tau C. V open BD 252 10 to 3 BD 1000 into 400 or 0.63 Newton per mm square. PT is 0.44 and tau C is 0.45. By the PT we can find out tau C. So here tau V is greater than tau C, so not safe. So our toe slab is not safe against shear. So what we have to do? We have to do either increase the depth or increase the flexure reinforcement to increase the shear capacity of the section. Now imagine our toe slab is failed at a shear. Toe slab is failed at the shear, right? So we have to follow some restriction like increase the depth or increase the flexure reinforcement for give us safety against shear. What we are doing? We are going to increase the depth or increase the flexure reinforcement on the toe slab. But in this case, we are just going to increase the reinforcement. How? Imagine tau V is equal to tau C. Imagine tau V is equal to tau C. So tau V is equal to 0.63. We assume tau V is equal to tau C. So 0.63 Newton per mm square. So we are going to reverse psychology here. Now this tau C equation we have to find out PT from IS 456 2000, page number 73, table number 90. Let's check these things. Okay. So in the IS 456 2000, page number 73, table number 90 is here. Okay, page number 73, table number 90 is here. Design a shear strength of the concrete tau C. So in the reverse psychology, what we done? We found the tau C. We assume tau V is equal to tau C. So we assume 0.63, but here is 0.62. But just calculate is imaginary. Okay. Now M20 grade concrete 0.62. If M25 grade concrete 0.64, M30 grade concrete 0.66, the value will be changed. But here is a M20 grade 0.62. So PT is 1. PT is 1. But for the 0.63, I assume PT is 1.05. Okay, so PT is 1.05. Now PT we found AST. So provide 25 mm dia at 110 mm center to center, and this gives the safety against shear. This thing gives the safety against shear. Now we are going to design a heel slab. Design a heel slab is a one-way continuous slab. Same thing for the stem. Okay, we done for the stem, right? We done stem as a continuous slab, but here slab designed as a one-way continuous slab. So pressure diagram we can draw for the hill slab. Weight of backfill and self weight of hill. So we can find out total downward load on the slab is 132 kilonewton per meter square. We can find out mu at here from this table IS 456 2000 page number 48, table number 12, right? So by this equation we can find out mu is 67.81, mu provided PT. To check for the shear design, is PT is required. To this side PT is required. So what I done it here, okay, imagine I calculate toe slab and we found the toe slab is fail at a shear. So for the safety purpose, what I done? For the safety purpose, I follow first find a tau v and assume a tau v as a tau c and find out the PT, okay? The simple things formula, okay? So Vu is 1.5 and find a tau v 1.5 WL by 2 60 into 28 into 2.7 divided by 2. So Vu is 122.06 kilonewton. So provide Vu upon Bd is a tau v equation. So its value is 0.28 Newton per mm square. And what we done, I say tau c is equal to tau v, I assume it. So 0.28 Newton per mm square is a tau c. So by the tau c, when we follow reverse psychology, provide PT is 0.50. So AST is 0.50 into 100. So 600 mm square. So provide 10 mm dia at 120 mm center to center support on the upper face. Okay, one design is complete. At support. Now we have a bar on the both side of the heel by 0.14 to L0. We calculate is development length. Here is just a development length we calculated, okay? So for the development length is 900 mm. Means we provide a heel slab in the vertical direction. Okay, I will explain the figure. Okay, give me a okay. So in the example you see there is a 900 mm development length is given. So what is 900 mm? Imagine here is a figure, it's a counterfort, purple color you can see, it's a counterfort, okay? And here is a stem, this is the stem and these are the base slab, right? So here is a connection between counterfort and base slab. We found 900 mm development length means it's given this. At the every counterfort we provide 900 mm extra length for the bar, okay? It's called a development length, right? You understand these things? So you understand what is 900 mm. Now at a mid-span design, mu is WL square by 24, 33, mu is 0.211. So provide 0.12 mm steel. Provide 0.12 percentage of steel. So AST by the 0.12 percentage is a 540 mm square. So provide 10 mm dia at 140 mm center to center. Provide 10 mm at 140 mm dia center to center. Now we have to find out distribution steel. So provide minimum 0.12 percentage of steel. Distribution steel 0.12 percentage. So provide 10 mm dia at 140 mm center to center on the lower face and as well as 10 mm dia at 140 mm center to center on the upper face. Now we are going to design connection of heel with a counterfort, means we are going to design vertical stirrups. So Vu is 1.5 into WL square, WL by 2. So shear force is 122.06 kilonewton. So AST is equal to VU by 0.87 Fy. So 338.06 mm square. So provide 8 mm dia at 2 legged vertical stirrups at 280 mm center to center. Okay. So this design is completed. Now we are going to design of counterfort. These things will show many complications. Design of counterfort is so complicated, right? So this figure I can explain in the drawing board. Just give me some time, okay? Yes, I draw this figure and give all the dimensions here, but I draw this dotted line here. You can see it's a dotted line, it's a triangle. So we are going to design the counterfort. So counterfort design is so simple, but sometimes it's become very complicated. Okay, in the counterfort you can see there is a depth is changing at every single depth, every single height of the counterfort. Okay, imagine if I assume this point, the depth is different. If I assume this point, depth again change. So by the change of depth of the counterfort, what happened? If change of depth of counterfort, what happened? Load is increased. So load increase, design is change. So in the counterfort design, we are going to design the counterfort in the parts, right? In the parts. But for the design, there is always load on the 19 angle. Okay, on the counterfort retaining wall, imagine all the time there is a load always in the cantilever, not a 90 angle. Okay, so for the calculate the load on the 90 angle, we have to find out the theta, angle of counterfort, which we cannot decide. It depends on the height of retaining wall. It's depend on the height of retaining wall and width of base slab. So we have to calculate the theta. So you can see here is a triangle. One triangle here. Triangle height is 7 meter. Width is 3.2 minus 0.2. 3.2 minus 0.2. So let's calculate the theta. Okay, I just move this here. Okay. So here is tan theta is equal to 3.2 minus 0.2 divided by 7 meter height. So tan theta is equal to 0.428, 0.428, right? So in the further way I found that theta here is 23.17 degree, right? We require this only. Okay, tan theta is equal to 0.428, right? For the now we are going to find out the height of the counterfort. This is imaginary triangle. You can see here this imaginary triangle. We need the height of this imaginary triangle. Why? Because of calculated depth is changed here. So we need this height. So we can calculate this height. So I just enlarge this triangle and put it here. Okay. Yeah. Now see, we found this theta. Okay. And the same triangle is here. So this theta will be same. Angle will be same. So same equation we will follow here. Which one? Tan theta equation. Tan theta equation. So tan theta is equal to tan theta is equal to 0.4 divided by this height, means small h. Small h. I give this all the details in the notes, you can read it, but this is the figure things. This calculation is depend on the figure, so I don't think to do this. Okay, Okay, so tan theta is 0.428 is equal to 0.4 into small h. So small h is equal to 0.4 divided by 0.428. So small h value is 0.935, right? 0.935. So we found the height. Right? So we have this height 0.935. Okay. Now we require all the depth of the counterfort. Okay. So I just draw one more figure in the bottom here. Okay, so here is 0.935 meter. Okay, it's the height of. Now what happened? Look at here. At the counterfort is some angle, and load is always at the 90 angle. On the counterfort, load is always at a 90 angle. So we have to find the depth at a 90 angle. We have to find out the depth of the 90 angle. What we do? We divide a counterfort into some parts, like, okay. So first is 0.935. Second part is 3 meter. Third part is 2 meter. And the last one is also 2 meter. So it's almost a 7 meter height. Okay, almost a 7 meter. Now what happened? We need this dimension. Okay, we require. Okay, now we have to find out the depth. We have to find out the depth, means we need to find this dimension. Right? We need to find this depth. So assume one triangle here. You can see this orange color. You can see the triangle, right? And we know the angle. We know the angle theta, right? So now we can calculate easily is bias sine theta. Sine theta is equal to capital D divided by 3 plus 0.935. What we done? We found the depth at the 3 meter. Assume one triangle. We have this height. We require this angle, right? This distance. So by the putting this equation, sine 23.17 degree is equal to capital D plus 3.935. So while solving this equation, D is 1.55 meter. Depth is 1.55 meter. Okay. Now assume there is a cover we provide is 80 mm. So we provide cover 80 mm. Therefore, small d is equal to 1.55 minus 0.08, because we provide these are cover, right? We provide 80 mm cover, right? So minus 1.55 minus 0.08, so value is 1.47 meter. Okay, these are the clear depth. Now we have to turn all this data, all this depth for the selected area. Now we going to enter. Okay, yeah, I put a wrong triangle. Yeah, so this triangle we have to study. We have to study this triangle. Same equation. Now first we done for the 3 meter. Now we going to the 5 meter. We divide the stem, or we divide the retaining wall as a particular we decide. Okay, there is nothing a perfect criteria. There is no perfect criteria how to divide a counterfort for the design. You can divide anything as you wish, right? So what we done, we divide 3 meter, 2 meter and 2 meter. Now I want to decide 1 meter, 2 meter, 2 meter, 2 meter. I can divide it. But this become a more lengthiest calculation. So first we decide for the 3 meter. Now we are going to find a depth for the 5 meter. So 5 meter we have the sine theta. Angle is same. All the time angle is same. D is same. D will be changed. So we have to find out the D. But one thing is height is 5 meter. So 5 plus 0.935. So here capital D is 2.335 meter. 2.335 meter. Right? 2.335 meter. Okay. Now we have find out 80 mm cover. So 2.335 minus 0.08 is equal to, value is 2.255. 2.255. These are the depth, right? Now we are going for the 8 meter depth. Okay, 8 meter depth. So here sine theta is equal to capital D divided by 7.55. This side is 7.55 plus 0.935. So here is a capital D is 3.34 meter. 3.34 meter. So that's why small d is 3.26 meter. So we found the depth for the all counterfort, for the whole counterfort. Now we can design it. So shall we start a design? Now you can see the figure which we draw. Same figure, same dimension, same value, right? So I just give the explanation how to draw this figure, how to find the data for this figure. But I'm calculated all the things in the notes. You can read it easily and understand it. Now we are going to design it. So first of all we design from the bottom at 7.55 meter depth from top. Pressure at base wall Ka into H. Put the value Ka 1/3, gamma 60, H is 7.55. So value is 14.26 kN per meter square. One counterfort carry load of 3 meter width. One counterfort carry load of 3 meter width. How this value come out? How this definition come out? Okay. How this length is come out? Okay. 3 meter width is load is carried by a counterfort. How? Let's. Now students, have you remember this, the spacing of counterfort while we finalize the dimension of the retaining wall? That time we give the spacing of counterfort is 3 meter. Spacing of counterfort between two counterfort is 3 meter. Now imagine there is a half portion. This half portion, this load is carried by this counterfort, and this half portion load is carried by this counterfort. And this happened in the both side. So this is the half, means there is a 1.5 meter and as well as 1.5 meter. So second time is here 1.5 meter. Same thing here, 1.5 meter. So total length is 3 meter. This load is carried by a counterfort. That's why I am writing a 3 meter. Okay. If spacing of the counterfort is changed at some time, the length will be changed. Right? Now how I hope you understand there is a why we carry the load is 3 meter width. Now we have to calculate load on the counterfort at a base. Load on the counterfort at a base. If there is a 14.26 into 3, because 3 meter width, so 120 into 78 kilonewton. So bending moment at a base on counterfort is 1/2 into 120 into 8 into 1/3 into 7.55. So moment is 1215.85 kilonewton into meter, and we have calculated by 1.5 multiplied by 1.5, so it's become mu. This is a factor moment. This is a factor moment. So we found a factor moment here. So by this factor moment we can calculate mu pt. Okay, now pt is 0.136, but for the beam with Fe 415 minimum pt is 0.20%. This thing is given in the IS code. Okay, so for the MPT required 0.2%, so AT is 0.2. So provided 7 numbers of bar in 20 mm diameter bar as a main steel. Now this design for the base. This is the design for the base. Now we are going to design for the 5 meter depth from the top. Same thing, just the height is changing. So load will be changed, bending moment will be changed, just change in the height, and we can found the PT, and last one we found 5 numbers of bars at 20 mm dia. Reducing the reinforcement means reducing the cost. Same thing for the 3 mm depth of the top. Height just change in the height, so that's why load changes, bending moment changes, right? Mu will be changed, so mu by pt will be changed, so ast will be changed. So provided 3 numbers of bar at 20 mm diameter bar, right? I hope you understand. Now one thing I am going to explain it here in the AST. Simple minor changes here. There is 300, it's a width. 300, it's the width, and 3260, it's the depth. The depth which we find here. For the 8 meter, we have a depth is here. Look at it, 3.26 in the mm is convert 3260, right? So this depth is taken, so that's why we require depth. Okay, so your design is completed. Now we have to design one vertical stirrups at a counterfort. Y is 7.55 meter. Loading on counterfort we calculated. So V is 1/2 120.78 into 7.55. Value is 4.55.94 kilonewton. So bending moment at 745 is 1147.46 kilonewton. So effective shear is VE is equal to V minus MB tan theta. V minus MB tan theta. So is 305. V is 455.94. M moment we find out 1147.46 and depth is 3.26.428. So VU is 457.59. It's a factor. It's a factor shear force, factor force. Then after PT we calculate rest divided by PT, so 0.225. So by the PT by the using IS 456 page number 73 table number 90 we can find out tau C. We can find tau C. Okay. Now there is a IS 456 2000 page number 73 clause number 40.4. We have one equation there. So in this example page number 73 IS 456 2000 clause number 14.4 we have a equation is VU minus tau C BD. VU minus tau C BD. So what is VU, tau C and BD? We all the things, okay? We all the data is there. So put the value in the equation VU minus tau C BD. Now VU minus tau CBD, VU is 457.93 into 10 raised to 3. Tau C is 0.4, 300 and 3260. So his force is 66.73 kilonewton. 66.73 kilonewton. Now VU is used for the find out the spacing. VU is used for the find out the spacing. Now this equation is IS 456 page number 73. Like here page number 73, 4 vertical stirrups spacing equation is here. VUS is equal to 0.87 Fy ASVD upon SV. Just interchange SV equation and we can find out. See this equation 0.87 Fy ASV upon D. Right, but ASP we have to decide. There is a 8 mm dia 2 legged stirrups. Consider 8 mm dia bar with 2 leg stirrups, so ASV is 100. So SV is spacing is 1173.20 mm center to center. 1173.20 mm center to center. Now we can find out minimum spacing of the stirrup required from the IS 456 to page number 48 clause number 12.5.6. This equation there. Now you can see here is a page number 48. We have equation clause number 26.5.6. We have equation ASV BSV laser greater or equal to 0.4 Fy. Right, so by this equation we can find out minimum spacing required. Okay, just remember the page number. You can, so you saw the equation are there, just remember the page numbers and clause numbers. Okay, you can easily find out the equation and the value we can write it down. Okay, 0.87 415 ASV 100 by 53.4, so it's 300 mm center to center. So horizontal stirrups provide to connect the stem with the counterfort 8 mm in front of center, which serve the purpose of shear enforcement of counterfort. Now our design is completed. Here are some sketches here. Okay. I explain all the things how to draw the sketch. Right? Here is a counterfort. You can see 300 mm center to center spacing, 12 mm dia, 210 mm, 8 mm dia, 160 mm center to center, 700 mm development length. right? Is the stem and counterfort connection. Second is 300 mm, 900 mm. Here is 10 mm. These are the stem and no, not a heel and counterfort connection. After this is a stem, heel, and toe slab alter design. Then here is a vertical stirrups and horizontal stirrups design. Right? Okay, this example is completed. I hope you will understand. And okay, so our example design is completed. I hope you will understand all the things and try it by yourself. So here's some practice example. Do it for the practices, and if not understand, just comment me. The counterfort retaining wall has to retain the earth with a horizontal top 5 meter above ground level. Means in this example, the first thing is retaining wall height is 5 meter is given. Density of wall is 60. Angle of internal friction is 30 degree. SPC of soil is 190. Coefficient friction is 0.6. Now we are going to determine the dimension of the retaining wall. Dimension of the retaining wall and check the stability of the wall. Okay. And design stem and dot diagram showing reinforcement details. So in this example, you have to follow 3 steps. First, dimension, then after stability, and the last one, stem design. You don't have to design a heel, toe slab or a counterfort. In this example, you just have to design a stem and connection between a stem and a counterfort and draw diagram. Simple. Whatever want to do it now. The conditions are always impossible. अपने लाइफ में जो भी करना चाहते हो ना कर लो, अभी शुरू कर दो. कंडीशन हमेशा इम्पॉसिबल रहेगी. इम्पॉसिबल को आई एम पॉसिबल कन्वर्ट करना आपको आना चाहिए. बाकी आपके लिए कंडीशन ऑलवेज ऑलवेज बी इम्पॉसिबल. Right? Okay. So our module 2 is completed, retaining wall design. In the next lecture we will starting a flat slab. Flat slab design is so easy. It will take some time for the understanding because in the flat slab design is little bit complicated. Just load transformation is complicated, but design is so easy. Okay. So we will meet soon. Till then, goodbye.